So yeah, good evening, good day. Like we have me, Simeon, and our supervisor Leonon K have worked on calibrating deterministic compartment models of infection dynamics using different methods such as neural networks and data sampling approaches. I'm gonna talk about these approaches and the efficiency of each the approaches, the methods we have used on compartmental models. So basically, compartmental models for infection dynamics are used to analyze and predict the rate of infection spread or in a region or something. And few of the compartment models are SCAR model. So here, what happens? The population is basically divided into compartments such as suspectable, exposed, infectious, and recovered, and the relation between these compartments are governed by some partial differential equations as mentioned here, like suspected cases depend on rate beta suspected infected, where beta is the transmission rate and where alpha is the inverse of incubation period. In a CR model we consider incubation period where a person who gets infected doesn't spread the disease immediately. He has some incubation time where he is like not an infectious guy, and like gamma is the recovery rate from infection, where the person from infected rate comes compartment comes to the recovered compartment. So for calibrating this SCR model, like we have this SCR model for infection for COVID-19 data, and we want to calibrate it with like different models to find the best parameters alpha, beta, gamma. So we tried to calibrate with Metropolis casting, one of the Monte Carlo methods, and physics informed neural networks and Latin hypercube samples. So Monte Carlo Monte Carlo Markov and Monte Carlo methods for like Metropolis casting are like random sample distribution. They are used to solve usually like differential equations or like integrals and everything. They usually draw random samples from the space, the number of draws we give. The and here we have used the mean square error between the our original and the predicted data to get the random samples of alpha, beta, gamma to get it minimum. And here physics informed neural networks are like similar to the neural network which uses like some physical laws, some physics laws. That's the difference, and they are like governed by some differential equations. And we also use Latin hypercube sampling. These are the methods to generate like near random samples in the multidimensional distribution. These ensures that like random numbers representative of real variabilities, whereas traditional sampling, like, these are like similar to the brute force methods. And for our experiment, we have considered the St. Petersburg data of the first phase, which was available in the from the free sources such as GitHub and like Kaggle. We have considered till July 30, 2020, because it was still like first phase in St. Petersburg. Using Metropolis hasting, the parameters we have obtained for like R naught T incubation, T infective were like for the our compartmental SCR model were these, and the R2 score was 0.72, which is like not too good. So we also tried with physics informed neural networks, but the main problem here was it was always approaching through the local minima, even we're trying to hyper tune the optimal parameters and everything. And with Latin hypercube sampling, after like generating some 10,000 samples, here there is a like the more samples we generate, the best accuracy we are getting. So it depends on we have like time complexity issues also here, and but we have got a better R2 score, nearly 0.95, with this Latin hypercube sampling, and we were able to predict the peak of the curve. And we are also in future gonna plan to do for multiple phases of COVID data, or like any infectious disease, because like most of the diseases have like multiple phases and everything. And using Metropolis And hyperspeed sampling, we are also avoided the problem of local minima. Yeah, these were our experiments for the compartmental model, and we have achieved good results with Latin hypercube sample. Yeah, that's all. Thank you for